sit in the device as an insert at the wall. So at this wall you have an anisotropic material, and that piece of material is subject to a strong magnetic field, so this is a permanent magnet. And this magnetic field causes that piece of ferrite to be not reciprocal, so that it's the propagation of a wave in one direction is quite different from a propagating wave in the other direction, which changes the wave pattern for those two waves, and the final result is that the wave propagates this wave, but it does not propagate that way. So if, for example, you want to send some signal to a device which is purely matched, and you do not want to cause standing waves in your circuit, you put there an insulator. The wave gets it there, it is reflected, but never gets back through this insulator. So this is a non-reciprocal device, something which is difficult to create at low frequencies. The last thing, sorry, I have used a different color. This is a circulator. A circulator, what is that device? Just again, it has a small piece of ferrite which is magnetized by a permanent magnet within this. You can see it inside. There is a chamber with a rod from ferrite. Try to show that into the other camera. So what this device is and how it works. Let's say that we have a circular space with the ferrite inside. Now this is again magnetized ferrite, which is not reciprocal. Now imagine that you have three ports, inputs or outputs, and due to the magnetized ferrite, there are different propagation constants in this direction or this direction. So let's say that the ferrite makes them twice the difference, and that this is 120 degrees in this direction. So it is again 120 degrees in this direction, but in the opposite direction you have a smaller constant, so say only 60 degrees. Now what happens? Well, that would not work. Let's say you have twice in this direction, so this is 240 degrees. Just the wave makes a 240 degrees change from here to here. So if we observe this picture, the wave comes in this way and it branches into two directions. One is running this way and makes 240 degrees, 120 and 120, and gets here. The other makes 240 degrees within this branch, so both waves have the same phase and they can get out by this port. What happens at this port? The first wave has 120 degrees, the second has 240 plus 240, which is 480. So 480 minus 120 is again 360, which is in phase, and you would get in this way a splitter that would run one part of the energy here and one part of the energy here. Now if you decrease this, if you get 90 and 90 and in the other direction 180, this would be in phase here but would not be in phase here. And by tilting the irreciprocity of the device, you can get to a situation where those waves add here and cancel here. And the circulator is a strange device, which is mostly denoted in this manner. This is the symbol for a circulator, which gets the signal from here to this port, and nothing gets here. If the energy enters here, it gets here, and nothing gets here. And if it gets from here, it gets here. So for example, if you have a generator, an antenna, and a receiver, then if you connect a generator directly to a receiver, you will destroy it. But this circulator can cause that the energy flows to the antenna, the reflected wave, for example from a target, from a plane, gets back to the receiver, and you can have only one antenna, which is called monostatic radar, the most used arrangement for a radar, and with a non-reciprocal material you can get a very strange device that gets the energy, just passes it, let's say, one output around the circle, so it gets energy from here to here, from here to here, and from here to here, but not in the other direction. So this is a kind of device that would be very difficult to realize in low frequency circuits, but it can be built at microwave frequencies, and it is called a circulator. Now I have shown you several pieces. Some of them are quite heavy, so I'm sorry I have not brought more of them. It was just one heavy bag. Normally I take students into a microwave lab and show them also other stuff there, which I invite you to come one day after COVID. So still, you are my students, and if you are interested in it, drop me an email someday later. I don't know when. But anyway, if you will be interested, I will be happy to show you the lab and those devices inside. Now please, we have been talking on waveguides with rectangular cross-section mostly. I have shown you some of the devices. I have spared one for the end as a small joke, but it's a real device. But now I would like to ask you for questions. I will look into the chat. Okay, so as there are no questions immediately, I will show you one device which is called a magic T. That's the official English term, a magic T. Well, what's the magic behind? Well, it is a device that has no non-reciprocal material inside. It's a piece of metal. It's a piece of metal that's arranged so that a wave that you put into this arm would be halved into this and this arm, and nothing gets here. But if you, of course, from the other side it works in the same way, so from here to here and here, and this property is the same for any of those arms. Energy incoming into that arm would be split in two other arms, while the third remaining will get zero. Then there is some fun about changing phases. Some of the waves are in phase, some are anti-phase. But anyway, the magic T is a piece of metallic waveguide that splits the energy into some parts and omits the other ones. And it's quite used to do some devices that exploit this nice thing. But anyway, a piece of poetry in technology. This is called a magic T. Now, last chance to, or close to last chance to ask about waveguides. After a break, you will have the really last chance, and then I will start with Smith chart. And just as I can see that there is a question on topics to be included in the final exam, we will do that in the third part of this lecture. So the second part with Smith chart is on the way, and now we have a right to rest for 5 minutes. So see you in 5 minutes.